In this video, I would like to introduce a new physical quantity. And to motivate this, I want to go back to the relationship between force and electric field. Okay, so recall that force is an interaction between pairs of charges. Meanwhile, the electric field, which is just the force divided by the test charge, is not an interaction between pairs of charges. The electric field is more of just a property of an individual charge. And there were some benefits to thinking about electric fields. So one is that we didn't have to commit to as much about the problem beforehand. We could think about an electric field for a single charge and then throw in a test charge later to figure out a force. It was slightly easier to calculate and so on. So there were a couple of benefits there. Well, what I'd like to do now is I'd like to do the same thing, but with energy instead of force. Okay, so now I'm going to define a new quantity V, where V is equal to U divided by a test charge. Okay, so just like with force, the electric potential energy, U, is a two-charge interaction. And we'll be able to think of this new quantity, V, as a property of an individual charge. And actually, just like we did with electric field, we'll be able to map out V around a charge. Okay, so at this point, I should tell you what V is called. And I'd like to preface this with an apology. I didn't choose this name, and I would choose just about any other name instead of this name. But V is called the electric potential. All right, so do not mix up electric potential with electric potential energy. These are two totally different quantities. They have different units, they have different names, they have totally different behaviors, but they have almost the same name. So it is important that you notice that electric potential and electric potential energy are two different things, even though they have very similar names. And even the variables are similar, so you'll want to make sure that in your handwriting, U and V look different. Okay, so for me, my U's will always have a tail, so you'll be able to tell them apart that way. I try to make my V's pointy as well, although when I write fast, that may not always happen. The bottom may get a little bit curved, but I make it a point to always have a tail on my U's. You should do something similar to that. You do not want to miss points because you can't tell your U's from your V's, and you don't want to miss points because I can't tell your U's from your V's. So these are two separate things. Just like you wouldn't want your F's and E's to look the same, you don't want your U's and V's to look the same. Okay, so what units does electric potential have? Well, we can figure out the units from the formula. So if V is defined to be U divided by Q, that's going to be units of energy, which are joules, divided by units of charge, which are coulombs. Okay, so a joule per coulomb is a volt, which is a capital V, just like the unit. So in addition to all the other things that are confusing, we now have a unit that is the same symbol as the variable. Again, not my fault. So We'll talk a little bit more about this in upcoming videos, but you've probably heard of volts before. They're named after Volta, which is the physicist who discovered, or maybe invented, depending on the way you look at it, batteries, although there is some historical evidence of batteries existing before that. But Volta did a lot of work in that, and so it makes sense that an electrical quantity was named after him.